Welcome everyone. So far in the series of videos we've been talking about equilibrium, we've talked about acids, and we've also mentioned how water can act as an acid or a base. But this video we want to just talk about water and what's going on. So if we have two water molecules, so just think about even your drinking water. This is pretty interesting here. And they react together. If they're both water, and we know they can both act as an acid or a base, then you can just pick one, right? One to act as the acid and one as the base. So I picked this first one to lose a proton because we know acids are proton donors. So it becomes hydroxide, negative OH. And then I picked the base to be the second molecule, and it's going to gain a hydrogen. So it becomes positive, and it forms hydronium. So you have hydroxide and hydronium. So I want to ask you a question here. So you form when water reacts with itself. Okay, notice our equilibrium is lying towards just the water molecules. Okay, but there is a small percentage that is going to dissociate or to react. Okay, and so hydroxide, what do you think of when you think of hydroxide? Okay, hydroxide, you should automatically think base. Okay, so we discussed how sodium hydroxide, we looked at potassium hydroxide, different bases. Okay, H3O plus, remember, that indicates to us acid. So whenever you see those two, think base, hydroxide, hydronium, or H plus, acid. Okay, so when we look at an equilibrium of these, we've learned that we can come up with equilibrium constants. We did that way back a while ago. And then we just previously looked at Ka's. Okay, Ka was specifically for looking at the acidity constant and comparing acidities. Okay, water has its own equilibrium expression constant, and it is called Kw. So that's pretty easy to remember because K is for equilibrium, okay, constant, and W, I just think of water. Okay, so if we look at what we've been doing with equilibrium, we take product concentrations divided by reactant concentrations. Well, since your reactants, if you look here, your reactants are water, right? Okay, so if we multiply both sides by water squared here, okay, then this yields what's called Kw. So basically it cancels out. Okay, and so we eliminate our water there. And so Kw is called the ion product constant. So you definitely want to know this. Write it down. If you're in my class, you're going to use a flashcard, so this is one you want to know. And this is equal to hydronium concentration. Right away, I think that's acid, right? Times the concentration of hydroxide. Okay, and that is what is a base. All right, so through experimentation with water, we know what these concentrations are. Since water is reacting with itself, we're going to have equal concentrations of hydronium and hydroxide, right? Because neither one's more acidic or basic because they're reacting together and they're the same molecule, water. So we know through experimentation that in your glass of water, if it's at room temperature now, so 25 degrees C, that we have 1.0 times 10 to the negative 7 molarity of hydronium and hydroxide. Okay, so look back and let's think about this in real terms. So this right here, we have equal concentrations of both of those, and that concentration is times 10 to the negative 7. So Kw, we can go further. Okay, so if we plug that in, so we know each of these is 1.0 times 10 to the negative 7 from experimentation. If we plug those in and multiply, we get Kw equals 1.0 times 10 to the negative 14. All right, so let's put that all together. Kw is a constant. It is equal to 1.0 times 10 to the negative 14 for all aqueous, in water, solutions at 25 degrees C. All right, so what we know from this and what you want to put on your kW equals hydronium times hydroxide concentration, but we always know this number, right? We always know it, okay? So we can use that. So just like any of our other calculations, if we know what kW is, and we know either hydronium, their acidic concentration, or the hydroxide, then we can always solve for the other, right? Okay, so here, if we wanted to find the hydroxide concentration of a solution that's got, it's not just water in this situation, okay, then we're going to take kW, which we know what that is, and we're going to divide it by what we know. So if we were given this concentration, so we have three different variables. kW, well, it's a constant, but three different things here. kW, hydronium, hydroxide. If we know two of the three, and we always know this, then we can solve for the other. Okay, so if you rearrange the equation to solve for hydroxide, then of course you divide by hydronium concentration, and that's what that is right here. So all that is rearranging an equation. So at this point, hopefully everyone can do that. Okay, if we're given the opposite, so in this situation, we want to calculate the hydronium concentration. So looks very similar. You take kW and you divide it by hydroxide concentration, and that's what is here. So you rearrange the equation. You always know kW, and therefore we can solve for hydronium concentration in this situation or hydroxide concentration. Okay, but of course we have to be given two of the three. All right, so let's look at two examples, and that will, after that, that will conclude the video. All right, so we have we're given the hydronium concentration of a cup of coffee, all right? And we want to find the hydroxide concentration. So anytime if you know one, you know the other, because you know kW, you know your ion product constant equation. Okay, so just like we did over here, so we're trying to calculate hydroxide. So if you look back, to calculate hydroxide, we took kW, 1.0 times 10 to the negative 14. It's a constant, it doesn't change, and we divided it by hydronium concentration. So that's what we're going to do. You would take kW, 1.0 times 10 to the negative 14, divide it by hydronium concentration, and you should get 1.0 times 10 to the negative 9 molarity. Okay, that is the hydroxide, so the basic, if you want to think of it that way, concentration. All right, I get calculator errors here. In your calculator, that's why I put parentheses here, more than likely you need to put this in parentheses and then divide and put this in parentheses as well. Okay, if you get a funny exponent, then it's a calculator error. Okay, so try to figure out your calculator and figure out what's going on. All right, so let's think about what this means. If you look at our hydronium concentration, okay, we know that water, our concentrations of hydronium and hydroxide is equal at 10 to the negative 7. Okay, for coffee, it's not neutral, right? Because it's not 10 to the negative 7. We have 10 to the negative 5. Okay, negative 5 is a much larger number than negative 7, right? Okay, so if this is larger, hydronium concentrations means acidic, then this is going to be acidic. Coffee is acidic. If you look at your hydroxide concentration, it's smaller than negative 7. Remember, negative 9 means you move your decimal place over 9 places, okay, to the left, therefore making it even smaller. Okay, so the solution, our coffee, that I love oh so much, is acidic. Okay, and so this is what I'm trying to explain to you. So when water is neutral, okay, and so hydronium is equal to hydroxide. It's not a basic, it's not an acidic solution, it is neutral. Okay, and so we have 10 to the negative 7 molarity of both. If your solution is acidic, you're going to have a higher H3O plus concentration, because remember, H3O plus means acid. Okay, if you have a basic solution, then your hydroxide concentration is going to be larger. Okay, and so it's going to be less than -7, or the negative exponent's going to be -6, -5, -4. Okay, it's going to be a larger number. Okay, so just don't let those negatives confuse you. All right, a practice problem that you will see. Okay, we are given, I'm just going to write out just a general idea. That the hydroxide concentration of a solution is 0.00001, or you could put that in scientific notation either way. Okay, and we want to find hydronium concentration. Okay, so once again, we can always find the other if we have one. Okay, so we want to look for H3O plus. If you look back at your previous slide, I'll show it real quick. Okay, we take Kw, we rearrange this equation here, which we know is equal to 1.0 times 10 to the negative 14. We take 1.0 times 10 to the negative 14, and we divide by hydroxide concentration, which is given. And our answer, so check it in your calculator, make sure you get it right, is 1.0 times 10 to the negative molarity. So our hydronium, think acid, concentration is 1.0 times 10 to the negative 9. Okay, I'm going to check that in my calculator just to make sure. 10 to the negative 14 divided by 0.12. Yes, 1 times 10 to the negative 9 concentration. Okay, so let's think about this. Is this solution, is it acidic or basic? Okay, I'm going to look at this right here. I see that hydronium is times 10 to the negative 9. Okay, I know -7 is neutral, right? That's what we've been saying over and over about water, and that means neutral. So -9 is a smaller number, right? So that means I have less hydronium concentration. So if I have less hydronium concentration, then it's less acidic, or it is more basic. It's not neutral. So if you look back at your chart here, to the negative 9, okay, so if your hydroxide concentration is larger, okay, then this here is going to be less than -7. Okay, and since it's -9, it's a smaller number, making the solution more basic. All right, I hope this helps. See you soon.